Alright guys, so today we're going to be talking about how to determine different characteristics of quadratic functions. So far we've talked about three different ways we can look at a quadratic function. The first way is in standard form. That's y equals ax squared plus bx plus c. And so that's one way we could see this. The other way is a vertex form, which is y minus k equals a times x minus h squared. And finally we have intercept form, which we haven't really named, but y equals a times x minus r1 times x minus r2. And so in each of these, the graph of each of these is a parabola, assuming that a does not equal 0. B or c could be 0, but if a is 0, then we wouldn't have anything squared, and so we wouldn't have a parabola. Now, in the first equation I have an a, b, and a c, which all tell me different things about the function, but the most obvious one is the a, which is actually repeated in the other two forms as well. And all three of those a's tell me the same thing. If a is positive, my parabola will open up like this. My parabola will open up like this. If my a is negative, my parabola will open down like this. It will open down if a is negative. If a is, the absolute value of a is larger than 1, ignoring the negative, then it's going to be a narrow parabola like this here. It's going to be very narrow, and that's either opening up or opening down, but very narrow. If my value of a is has an absolute value that's less than 1, so somewhere between 0 and 1, it's going to be very wide parabola like this, or like this here. So those are my possibilities. B and C in standard form are a little bit less clear as to what effect they have directly on the graph. In vertex form, A we already mentioned, and H, K are the coordinates of my vertex, which is certainly an important point to know in the parabola, so that's going to be worthwhile. And in intercept form, R1 and R2 are the two solutions to the equation y equals 0. They're my two x-intercepts. They're the two roots of the equation. That's why we call it R1 and R2. Anyways, that's something that we could see. And all three of these forms can tell us all the same information, actually. Sometimes it's a little bit easier to find one thing than the other, but we can determine the vertex, the axis of symmetry, the zeros, the domain, and the range from each of these forms. So let's take a look and see exactly how we would do that now. All right, so first, since we've been doing this most recently, let's look at vertex form, which, as a reminder up top, that's y minus k equals a times x minus h squared. And so the first thing I can actually find here from my example, which is y minus 4 equals negative 2 times x plus 1 squared, is, not surprisingly, the vertex. This is vertex form, so I'm going to get that from the 1 and the 4. And remember, I'm basically looking to see what h and k are, and h and k are being subtracted from x and y respectively. So if this is a plus 1, that means I must be subtracting a negative 1 for my x coordinate, and I must be subtracting a 4 for my y coordinate. So negative 1, 4 is my vertex. That's what I get from there pretty easily. Now for the axis of symmetry for all these parabolas is a vertical line that passes through the vertex, so the only possibility here is going to be x equals negative 1. Kind of an ugly x there. Let me see if I can clean that up a little bit. There we go. That looks a lot nicer. Now, domain for all of these is going to be the same. The domain is just going to be all real numbers. So don't get that wrong, because I will never forgive you. The domain is just always going to be all real numbers. You can plug in anything for x and make it work. Now, your range is not going to be all real numbers. This is a parabola, so it's going to be limited. And the way we figure it out is based on two things. We base it on the y-coordinate of the vertex, because range has to do with y, and it has to do with my value of a. In this case, a is negative. Because a is negative, I know my parabola opens down, like this. It's also going to be narrow, but I'm not too interested in that. But because it opens down, I must have a maximum value at the peak. And and that maximum value would occur at the vertex. That maximum is going to be 4, which means that my range is going to be everything 4 and below. The way I write that, I just say y is less than or equal to 4. And so for range, the way that it opens is going to determine whether it's less than or equal to or greater than or equal to. For these problems, we're always going to have the or equal to, so you really just have to determine if it's going to be less than or if it's going to be greater than. All right, so then the last thing that we have is the zeros. And the zeros here are going to be based on what we can have to make the x-intercepts of this. Now the x-intercepts we know happen when y equals 0. So I'm actually just going to replace the y in my equation with 0. So I'm going to have 0 minus 4 equals negative 2 times x plus 1 squared. Certainly on the left side, that's just negative 4 equals negative 2 times x plus 1 squared. And now this is very similar to the type of problem I'd have from completing the square, except that the square's already been completed for me. So I'm going to divide each side by negative 2, and that's going to leave me with 2 equals x plus 1 squared. I'll take the square root of each side. Now I'm just going to rearrange the order here. I'm going to put x plus 1 on the left, and that's going to equal plus or minus the square root of 2. Now one thing to keep in mind here when I subtract 1 from each side is to put that negative 1 in front of the square root of 2, in front of the plus or minus. So those are my two zeros. I've got negative 1 plus or minus the square root of 2. But graphically, it's probably useful to have a good approximation for that. And so I might remember that the square root of 2 is approximately 1.4, just for the sake of it. So negative 1 plus 1.4 is approximately 0.4. And negative 1 minus 1.4 would, again, because the 1.4s are approximate, these are my two different values that I'd have here. That's going to be negative 2.4. And so when I have my zeros listed there, I know that approximately I'm talking about 0.4 and negative 2.4, at least approximately. And so all of this information is something that I got just out of my original equation, really, and just then a little bit of algebra. Let's confirm this by taking a look at the graph of this function. You can see the vertex is indeed at negative 1, 4. That's what I expected. Axis of symmetry would be this vertical line, x equals negative 1. You can see the parabola is symmetric around that. The domain, well, since this parabola is going on and on, both down and out forever and ever, it will be all real numbers. The range is everything less than 4. Here's 4 at the peak. That's the y value that's the highest. Everything else below it will be covered. And the zeros, we see negative 1 plus or minus the square root of 2. Well, certainly on our graph, we're going to be better off checking out with our approximate values. And 0.4 is a pretty good estimate of that, and negative 2.4 is a pretty good estimate of that. It looks like it's not quite halfway between 0 and 1 and negative 2 and negative 3. So that seems like a pretty good fit. And so there you have it. That's how you use Vertex Form to analyze the graph. Okay, next we have standard form. This one is a little bit more work, but sometimes this is what we have. The first thing we're actually going to be able to find here is the axis of symmetry. And the axis of symmetry comes from using the formula x equals negative b over 2a, which is part of the quadratic formula. But in this case, my b is going to be 2, my a is 1, so that's negative 2 over 2, which is negative 1. So my axis of symmetry is the vertical line, x equals negative 1. Now in order to find the vertex, I'm actually going to put that value of negative 1 into my equation. So I'm going to have y equals negative 1 squared plus 2 times negative 1 plus 3. Negative 1 squared is 1, plus 2 times negative 1 plus 3. Now I'll do the multiplication. That's going to become a minus 2. So 1 minus 2 plus 3. And I get y equals, let's see, 1 minus 2 plus 3, that's negative 1 plus 3, which is 2. So my vertex is the point negative 1, 2, because my vertex has to sit on my axis of symmetry. And when I plug negative 1 into my equation, I get 2. So, filling in the rest of the information I can. Domain, I already know it. It's all real numbers. And the range, my a value here was 1. So that means my parabola is going to open up. If it opens up, it must have a minimum. So for my range, I say y is greater than or equal to, and I look at this here, 2. So y is greater than or equal to 2. Now the zeros of this function are going to be, again, the x-intercept. So I set y equal to 0. And so I have 0 equals x squared plus 2x plus 3. Now I might try to factor that to solve it. It's not going to be factorable. I'm actually going to want to use the quadratic formula. So plugging into x equals negative b is 2, plus or minus the square root of b squared is 2 squared, minus 4ac is 4 times 1 times 3, all over 2a, which is 1. So let's give ourselves a little bit of space here, and then we'll come back to express our answer nicely here. So it's going to be negative 2 plus or minus the square root of 4 minus, I think that's 12, over 2, negative 2 plus or minus the square root of negative 8 over 2. And this I see is going to actually involve I. I'm going to have, if I simplify the square root of 8, square root of negative 8, it's going to be 2 rad 2 I. And because everything's over 2, I can cancel a whole bunch of stuff. And I'm looking at negative 1 plus or minus rad 2 I. And so those are my zeros there, which are not real. Let's take a look at what that would look like in the graph, because if I go back up here and I say that my zeros are kind of none, because I'm really only interested in the real zeros, when I look at the graph, now it starts to make a little bit of sense. I can see my vertex is at negative 1, 2. My axis of symmetry, x equals negative 1. Domain, yeah, I'm going out forever, so that's all real numbers. Range, greater than or equal to 2. But I have no x-intercepts. That's because this parabola opens up, but its vertex is above the x-axis. So it makes sense that my zeros were imaginary, because there's no real point that I'm going to hit this this number line here. So just by analyzing the graph, we actually maybe could have figured that we had none originally, knowing that the range was everything greater than or equal to 2, so y was never going to equal 0. But worth doing anyways, worth practicing with the quadratic formula just to practice it. All right, so that's using standard form. We have one more to go. All right, so last one here is the intercept form. This is where I'm given the 2 x-intercepts, and I go from there. So in this case, I have y equals 1/2 times x plus 4 times x minus 2. And in order to figure out any of this information, I want to think about what's going to be easiest. Well, probably the easiest one first is the domain, since I told you that's always going to be all real numbers. The easiest after that is actually going to be the zeros. And so for the zeros, what I do is I take my 2 expressions with the x's here, and I split them up, and I set each one of those equal to 0. Because really, I need to come up with some way to make my y equal 0, and that's only going to happen if one of these two things is true. So the first case, I have x equals negative 4. The second case, I have x equals 2. Those are going to be my 2 zeros here, 2 and negative 4. You can write them in either order. So that's going to be kind of where we're starting there. We don't need to worry about quadratic formula because this is something that really was already factored for us. After that, I'm going to be able to find the axis of symmetry because the axis of symmetry is always going to be right in between that 2 and the negative 4. So I'm going to find the average of those two things. So I have 2 plus negative 4 over 2, which is, let's see here, that's 2 plus negative 4 is negative 2 over 2 is negative 1. I promise you this was a coincidence that all three of these had the same axis of symmetry. I truly just made up the problems and didn't expect that to happen. It must be a sign. X equals negative 1, something. I don't know what it means. But anyways, now that I have that, I'm going to take the x equals negative 1 and plug it into my equation. And something nice should happen here. When I plug it in, I get negative 1 plus 4, and then negative 1 minus 2. Now, the negative 1 plus 4 is going to be 3. The other one's going to be negative 3. If we've done it correctly, these numbers here should be the same, except one's going to be positive, one's going to be negative. So we're going to have 1/2 times negative 9, which is negative 9/2. You can think of that as negative 4.5 or whatever, negative 4.5. But I'll leave it as the improper fraction. So my vertex is negative 1, negative 9/2. That's what I have there. And then the last thing I could probably find here is the range. And so the range is going to be connected to the fact that my value for A is positive. So my parabola opens up. It's actually going to be opening up and wide. And therefore I have a minimum value at negative 9/2. I must have everything above it then. So my range is y is greater than or equal to negative 9/2. And so let's take one last look at the graph here. And you can see that everything matches up. There's my vertex, negative 1, negative 9/2. Axis of symmetry, x equals negative 1. Domain checks out to be all real numbers. Range is everything greater than or equal to negative 9/2. And the zeros are located here at 2 and negative 4. And that's about it. Pretty straightforward when you just realize that there are different ways to express the same information, and you can go from there. It is possible to convert from one expression to the other, and I'll mention that on, or one form to the other, and I'll mention that on the last slide here. So just one last note, if you have a particular form and you'd like it to be in another form, there are a couple of things you can do. If you're starting in standard form and you want to get it into intercept form, what you'd need to do is you'd need to try to factor. Now, that may not be possible, in which case it's probably not worth trying to put it into intercept form. You could technically do it by using the quadratic formula and figuring out the x-intercepts in their irrational and possibly imaginary forms, but probably not worth it. If you have standard form and you want to get it into vertex form, then what you need to do is actually complete the square. And so sometimes that's easier said than done. It's easiest if our A is pretty small, like 1. It's doable otherwise, but it's a lot. Sometimes it can be a little tricky, but it definitely is a way to do it. Now, if you have either intercept form or vertex form and you want to get that into standard form, that's probably the easiest. That just involves multiplying, but making sure that you FOIL if necessary. So when you do that, you'll end up getting an expression that can be rearranged pretty easily to get it into standard form. There's no easy way to go from intercept form to vertex form. You can do it, but without fully analyzing the graph, it's pretty tough. If you're really interested in doing it, probably your best bet is to go first into standard form and then go to the other one if you want. So you can, from vertex form, you can FOIL and then factor to try to get into intercept form, or vice versa. For intercept form, you can multiply or complete the square to get into vertex form. Just a little note in case you wanted to switch them around, but that's all you have to do. All right, hope this makes sense.